Hello, doing a little walkthrough for basic trigonometry and the theorem of Pythagoras. Should be useful to answer an awful lot of trigonometry questions. It's a very good introduction, so fingers crossed it's helpful. Focusing on trigonometric ratios, so these things are sine, cosine and tangent, and they're abbreviated sine A, cos A and tan A. A here stands for the angle in a triangle. So we're talking about triangles and we call it trigonometry. And these are three ratios we're looking for. Some of the words we're going to come across a lot are hypotenuse, opposite and adjacent, so I will explain those words in a moment. And the five things we're trying to learn really are how to label the sides of a triangle. We want to learn a memory tool that's going to help us remember our definition for sine, cos and tan. So we're going to do the memory tool and the definitions. Then we want to look at the inverse functions, so inverse of sine, sine inverse, cos inverse, tan inverse. And we want at the end to put in some practice of Pythagoras theorem, or the theorem of Pythagoras, which is looking at the side lengths of triangles. So our first learning intention, labelling the sides of a triangle. And the first one we should always label is our longest side. So we should always label the longest side is the hypotenuse. In a right angle triangle, that'll be your diagonal one. Another thing to notice is that it's across from your 90 degree. Okay, so it's the longest side. Usually that's sufficient to figure out which one we're on about. Before we go naming the other two sides, you see we've got question marks there. We can't really name them unless we specify an angle. So we need an angle before we can label the remaining sides, opposite and adjacent. So here's what I mean in these triangles over here. In our first triangle we have angle A. So imagine you're in a weird triangular room and you're positioned here in the corner. You're positioned in here and you put your back to the corner and you look out across the room. The wall you're looking at is opposite you, so it's opposite angle A. Okay, so that idea, you get yourself into the corner, you look across, the side that's across from you is the opposite you. And so this remaining side is the adjacent. Remember that the longest one was the hypotenuse. Should have said that at the start. So looking at the second triangle, again, we label our hypotenuse first, the longest side, and then you position yourself maybe in the corner here of this weird triangular room. You look across the room, you can see this side is opposite from you are, so it's opposite angle B or opposite position B, and that means then that the remaining side has to be the one that's adjacent to position B. So that's straightforward enough. Causes a lot of trouble though, so practice is what we need. So let's practice labeling sides a little bit. I'm going to start again by labeling the longest side, the hypotenuse. And again, look at this green work here. If you're a little unsure sometimes, which we will be, so occasionally be a little unsure which is the longest side, then you just kind of position yourself in that corner at the 90 degree and look across, because the longest side of the hypotenuse is always opposite that 90 degree triangle in a right angle triangle. So I must say is that we are talking about right angle triangles, we're not talking about other types of triangles at the moment, only talking about right angle triangles. So which side is our hypotenuse? Well, in this first diagram you can see one is clearly the longest, that's the hypotenuse. Triangle B, side 2 is the hypotenuse. Triangle C, side 1 is the hypotenuse. Triangle D, a little harder maybe, it's side 3. Again, if you're unsure, position yourself at the right angle and look across, that's the side you're looking at there, the hypotenuse. Definitely triangle E is getting harder. I wouldn't be so confident. I'd want to position myself again in this weird triangular room at the right angle and look across. So that is my hypotenuse, or the longest side. Triangle F is easy enough. Side 3 is the hypotenuse. Triangle G, there's no hypotenuse here, it's obvious. We can't tell, so I wouldn't even try to label one of those hypotenuse. Also, like I said, we're looking here for sine, cos and tan. We're looking at right angle triangles. We're not interested in this type of triangle here. So triangle G, we're not interested at the minute. Okay, continuing with this idea again and going back to the point that once we've found a hypotenuse, okay, that's the easy one, we need to figure out which angle we're talking about and therefore what side we're opposite. Imagine again just, well, the words here, adjacent means beside, while opposite means across from. So imagine someone in your house is leaving the house and they can't find their keys. They said, "Can I even see my keys?" And you say, "Yeah, your keys are opposite." that would not be very useful, and they wouldn't be too impressed, because you need to say opposite what. You need to know what is it beside or adjacent to, or what is it opposite from. So we don't label the sides opposite and adjacent, we say opposite angle A or opposite angle B. And we can see in these two triangles that, while this side is opposite angle A, the side at the bottom is the one that's opposite angle B. So opposite moves around. Look in the room where you're sitting right now, what's opposite you. If you move to a different position in the room and consider what's opposite, the thing that's opposite changes. So we have to think about where we're standing. Are we at angle B or are we at angle A? So let's take a look. So again, it's quite clear that we can see that the hypotenuse is that length there. So you can see opposite A is labelled and adjacent A is labelled. So now draw and label the following triangles. Pause the video if you want and just sketch them out. So we're going to pick out our hypotenuse first. That's easy enough in each triangle. So that's kind of straight away, easy, easy, easy. Last one, not so easy. Remember, if you're not sure, position yourself at the 90 degree and go across. Here's our hypotenuse. Okay, so we've labelled our hypotenuse in each triangle. Now we need to position ourselves at the labelled angle. So angle A, this is my opposite. This is opposite angle A. I need to say what it's opposite. Okay, position myself at angle A. That's opposite A. Position myself at angle A. This is opposite A. Position myself at angle A. This is opposite angle A. Position myself at angle B this time. And this side is opposite B. So that was easy enough with a little practice. We can see that the side that's left in each one is the adjacent, so adjacent A. This side is the one that's left, it's the adjacent to A. You'll notice that the hypotenuse is also adjacent to A, but, well, the hypotenuse is the longest one and it gets a name already, has a name, hypotenuse, so don't need to label it again. So this side here is the one that's adjacent. So when we say it's adjacent, we kind of mean, well, it's adjacent, but it's not the hypotenuse. And so we have the adjacent, bit squashy here, adjacent A. And again, from the position of angle B, what's adjacent? Well, it's the one that hasn't been labelled yet. Again, might be a little hard, but we've already named the hypotenuse. We've already named the opposite, so it shouldn't be so hard to figure out the adjacent. It's the third and remaining side. So this should be getting kind of easy. So let's just drag these into the right spot. We kind of already labelled them there. Opposite A. Oops. And adjacent A. So hopefully that's easy enough. Next triangle. What have we got here? So our hypotenuse is already labelled. And so we think opposite B, opposite B. So I'm in this weird triangular room. Put it back to angle B. This is my opposite. Let's slide it across. So again, I know the hypotenuse, I know the opposite. It's very clear. The adjacent is here. Does it make sense? Let's double check. Well, yeah, again, if I'm at this corner, I've got two sides equal to me, but one of them is already labelled hypotenuse. So this one's the one we're going to label adjacent. So not so bad. Let's on to the second learning intention here, which was to have some sort of rhyme or way of remembering the definitions. The definitions are down here. We'll come to them in a second. So we just need a rhyme to help us remember them. So we have silly, old, Harry, caught a herring, trawling off America. This is sine is equal to opposite over hypotenuse, cos is equal to adjacent over hypotenuse, and tan is equal to opposite over adjacent. So we have a way of remembering our definition that we're going to come to. Lots of people just learn this as Sakatoa. I don't like that myself, but maybe you do, Sakatoa. I do really like the one the Khan Academy has, some old hippie. So some old hippie is sine equals opposite of hypotenuse. Caught another hippie, that's cosine is equal to adjacent over hypotenuse. Tripping on acid, that's tan is equal to opposite over adjacent. So some old hippie caught another hippie, tripping on acid. But the one I learned myself, and I find easiest to remember is silly old Harry caught a herring trawling off America. Okay, so these are the formal definitions. We kind of mentioned them there a second ago. Sine of the angle A is just the length of the opposite divided by the length of the hypotenuse. So it's just one length divided by another. The same goes for cos. This time you're dividing the adjacent by the hypotenuse to get what we call cos of A. And the last one, take the opposite length divided by the adjacent length and you get tan of A. Some of you might have already noticed that, well, dividing the opposite by the hypotenuse, that's the same as the rise over the run. If you've learnt that already, great. If you haven't, no worries, you don't need to know it today. But it's nice to realise that tan A is the same as slope or rise over run. Okay, so that's all they are. It's just the lengths of three sides and we're just dividing two of them. So that's easy enough. Let's take a look at this triangle here. We have some work. We're going to stick with this green box. Well, black box should say with the green work. So we've labelled the hypotenuse, opposite and adjacent in the triangle. So now sine, we're told from our definition, is opposite of our hypotenuse, or silly old Harry. Reminds us that sine is opposite divided by hypotenuse. So our opposite is 6 and our hypotenuse is 10. You can see that in the diagram. The opposite was 6 and the hypotenuse was 10. Just divide those, you get 0.6. So sine of angle A is equal to 0.6. I know you're kind of wondering what does that mean? We don't really know yet. At the moment we're just going to keep it simple. Cosine of angle A, we'll take a look at that one. So it's the adjacent divided by the hypotenuse, or again caught a herring, or whatever rhyme you've remembered, but cos is adjacent divided by hypotenuse. So the adjacent is 8, the hypotenuse is 10, so fill that in. 8 divided by 10 is 0.8. So in this particular triangle, we divide the adjacent by the hypotenuse, we get 0.8, and we call that cos of angle A. And we'll learn more later, keeping it simple though. Okay, so tan of angle A is the opposite divided by the adjacent, so it's 6 divided by 8, that's 3/4 or 0.75. Few things to know. Again, these only work in right angle triangles, so I really should have wrote that down somewhere. So these are only for, or only to be used in, right angled triangles. So right angled triangles, very important that we only use them in right angled triangles. Now most of your simple trigonometry problems will be right angled triangles, so it's going to be kind of easy. Now to use these in the calculator, let's say you're just told to find the sine of 40 on a calculator. So this is the work in black at the bottom here. So sine 40, just type it into the calculator, it couldn't be easier. It should give you this decimal. Make sure your calculator is in degree mode, it should have a little D at the top. If it's not in the degree mode, if you don't see the D, you might have a G or even an R at the top of your screen somewhere. Hit the mode button, or on the Casios you want to go shift and then mode, and it brings up 8 options. So you want to pick number 3 for degree if you're using the Casio. And just make sure you're in degrees. So sine 40 should be that. Try tan 60, it'll tell you root 3, or hit that SD button on the Casios. It's 1.732. Your cos 20 should be 0.93969 and a few more decimals. Sine 90 should be exactly number 1. So yeah, you can use the calculator. So if you're asked to find sine of a given angle, you can get the decimal, or if you're given the lengths of the sides in the triangle, you can use those lengths to find the ratio or the decimal. So we've got 2 different ways to get the decimal. If we know the angle, throw it into the calculator. If you have the length of the sides, we can divide them. This is actually really useful for all sorts of things. Any sort of rocketry will rely on sine and cosine, even pulling and dragging material, to make a building or so on. Or it's very useful for all sorts of things, guiding boats into port. It has endless uses. It's really, really great stuff. So as we go on, you might get a chance to look at questions where you see how useful this is. Okay, so inverse functions. So this is the opposite of sine, cosine, and tan. So inverse sine will cancel sine, inverse cos will cancel cos, inverse tan will cancel tan. So let's take a look at our green triangle here. I've got a set of green examples and blue examples. Okay, so the green triangle here, we're working from angle B. I see that I just somehow deleted my sine there, sine B. Okay, so working from angle B, we already have the hypotenuse, opposite and adjacent labelled. You can see the sine B opposite of our hypotenuse 8/10, and we don't, we want to find B using our calculator, so we're going to get what's called inverse sine. So again, to do this, you're not going to need to do the bit on the left hand side. I mean, these will always cancel, so you can see they're gone. Okay, so you're going to be left with only an angle on the left, but on the right hand side, that's the bit you can do with your calculator. So hit shift, then the sine button, and you should see the sine with little -1 on the screen. Put in your fraction 8/10 or your decimal 0.8, whichever, hit your equals, and we should be getting this angle. Again, if you're not getting that angle, just check, are you in the correct degree mode? You don't want that little D on your screen, okay? Do the same for cos. So again, shift, the cos button, this time 6/10, because cos is 6/10. Should get the same answer, because the angle doesn't change in size, the angle is still the same. And if we use tan, it's opposite over adjacent, so it's 8/6. So we see where we get the 8/6 from. They're coming from the triangle, the 8 and the 6 and the triangle. So that's where they come from. Oops, a daisy. Okay. So again, you want to get your inverse tan. So just like we did inverse cos, using inverse tan on both sides. The left hand side, you don't have to put that into the calculator. They'll just cancel each other. They'll disappear first because they're opposite. One function does the other. On the right hand side though, we can do this in the calculator. Shift tan and then 8/6 as a fraction, or you can already do 8 divided by 6 in a bracket or whatever, but you want to hit shift and tan, 8/6 equals, and it should be giving us the same answer. Again, make sure you're in degree mode for these. Right, the blue examples there, you can pause the video and just check all of those. Again, you'll just see we're getting the inverse sine on both sides, the inverse cos on both sides, and the inverse tan on both sides. We usually don't show that middle line. You don't have to. You just need to be able to do it on the calculator, really. But it is nice to see that we do the same thing to both sides, like in any other equation in maths. So a little reminder there of our Sokotoa, or your silly old Harry caught herring trawling off America in the purple. We're going to use that in our question here. We're asked to find the size of the angle beta. So beta is like a B with a tail on it. So let's label our triangle first of all. So our hypotenuse is the longest side, that's 8. If I'm standing in the weird triangular room in the corner, I look across into the room, I find my opposite what? Opposite angle beta. Should have a beta there. And so the last side must be the side that is adjacent to beta. Okay. So we have our trigonometry ratios down here. Our definition, that symbol is just theta for an angle. Could have used A for angle as well. Just thought I'd throw in theta because it's quite common. So which one of these should we use is often the question. Often we don't know what to use. Depends on the information in the question. So let's look at the question. I look at the problem. We do know the angle is beta. Well, we kind of want to know that angle. So we definitely need a formula with an angle. That's a good thing because all three formulas have an angle. We do know the hypotenuse. Okay, so we can tick that. We know the hypotenuse. I do know the opposite. That's 5.5, so I know the opposite. I don't know the adjacent yet, so that's no good to me because I don't know it. So we can see that cos and tan, they both have an x on them. They're not so useful. The formula that's going to be useful to me right now is sine, because I've got 3 ticks. Okay, so I can use the formula with the 3 ticks. Let's put my numbers in there. So sine of theta, so in this case sine of beta, sine of the angle, is equal to the opposite, which is 5.5, divided by the hypotenuse, which is 8. So some people like to get the decimal straight away. If you do though, keep it on your calculator because don't round it off. So it's the same as 11/16, or if you actually don't round off. Okay, so here I'm going to have to round off. Oh no, I don't actually. It's a nice decimal. So 4 decimals is full accuracy here. Great. So now that's what we found sine beta is. Now, most people prefer the decimal, so I'll go with that, but it really doesn't make any difference. You can keep your fraction on your screen, which is kind of a good habit to get good at fractions. It really does make your life easier in maths. So now what are we going to do? We're going to get the inverse sine of both sides. So inverse sine, doing that on both sides. So inverse sine of sine beta on the left, and on the right it's inverse sine of 0.6875. Get in the habit of saying that inverse sine so you get comfortable with the language. I suppose these are going to cancel each other out, so I'm going to be left with only beta. So don't need the calculator for that. But I do want my calculator for this here. I'm going to hit shift sign, type in my decimal, equals. So shift sign 0.6875 equals, what's that going to work out as? Works out as 43.43253656 blah blah blah, perhaps. Okay, so it's in degrees. So if I want, let's say, 3 decimals, it would be 43.433, correct 3 decimals. Okay, so I found my angle. Again, make sure your calculator's in degree mode. Look for the D on the screen. Okay, so that's kind of bring us to the end of the sine, cos and tan part, the trigonometry ratios. We're looking at the Pythagoras here, and I'm just saying call Pythagoras or theorem Pythagoras or Pythagorean theorem. Only works in right angle triangles. So important, I've repeated it twice. So that's kind of very similar to the sine, cos and tan. They were only for right angle triangles as well, yeah. So really this whole video is about right angle triangles, really. Okay. So if it only works in right angle triangles, can we use the theorem of Pythagoras in these particular triangles? Okay, so we have a right angle triangle here. Yes. B, it's a right angle, so yes. C, I don't know if this is a right angle or not, so for the moment I'll have to say no, can't use it. Triangle D, yeah, that does have a symbol, it's telling me it's right angled, good. Triangle E, yeah, 90 degrees, we can use that one. F, maybe, let me think. 180 for a full triangle, take away 45, take away 45. The last angle is, of course, 90 degrees. So because this top angle is 90 degrees, yes, we can use Pythagoras' theorem in this one. So just look out for questions like that. Pythagoras' theorem is often visually shown like this, okay? And we see a kind of definition given down the bottom of the page, and we're going to try and figure out what does this definition mean. Okay, so we can see that triangle, it's in the middle of the page there, it's 5, 4 and 3 long here. Okay, so if you get the square of 3 by 3 is 9, so I kind of get 9 here. If I get the square of 4, I get 4 by 4 is 16, so here, you know, see the 3 squared and the 4 squared over here, down here. Okay, so 3 squared and 4 squared. Okay, so we got 9 out of that one, we got 16 out of that one. So that should be equal to the longer side, hypotenuse on its own. 5 squared, 5 by 5 should give us 25, so there's 25 boxes there. So yeah, we're saying basically 25 is equal to 16 plus 9, so it's really kind of easy. Just add the two smaller numbers, to 16 to 9, you should get to 25. So essentially what have we done? We've just squared all the sides of the triangle, that's all we've done, okay? So we're just squaring all the sides in the triangle, so it's no big deal. Sometimes, you know, people say if you square all sides, that A, B and C in the definition diagram, okay, here's our definition diagram. So if you square A, B and C, we're just saying that the long one should be on its own over here, and the two short ones should be together getting added up. Okay, so the long side squared is equal to short squared plus short squared, some people say. Okay, anything that'll help you remember it. Wikipedia has a nice little visual on this in a section called Pythagorean triples. So here we can see a triangle, side length A, B and C. A is the shortest one, it's only 3 long, 3 by 3 is 9 in the kind of peachy, pinky boxes. Side length B is 4 long, so it's 4 by 4, give you 16 green boxes. And in side C, you can see it's 5 boxes long, but they've kind of color coded them so you can see where this, you know, where the 25 is coming from. It's coming from 16 green and 9 peaches, kind of pinky peach. So we can see that we've got 9 and 16 equals 25. So it's a lovely visual way of looking at it. Okay, so that's kind of the definition part of it. It's a wee bit messy, but it's okay, hopefully. So that's just kind of neat and tidy, showing you the definition the way it might appear in a textbook or something. So the C is the one on its own, it's the hypotenuse, and the two shorter sides are A and B. square all three of them. Two smaller numbers add up to give you the bigger number. It's kind of easy enough. So here we have a nice triangle here, and it's right angle. We can see it's marked as a right angle triangle. Side lengths 26, 24, and 10. We're squaring all of them. So we're squaring the 26, squaring the 24, squaring the 10, and the two smaller ones are getting added together. So what is 26 squared? Let's see, does this thing work? 26 squared is 676. 24 squared is, no harm in getting your own calculator, 576. 10 squared is 100. Yeah, that adds up, that's true. 767 is equal to 676. So yeah, that's true. So Pythagoras' theorem definitely works with this right angle triangle, that the longer one squared is equal to the two shorter ones squared and added together. That's all it's saying. Let's use this to answer a question. So we have a triangular sail needs to be repaired. Find the length of the side marked X. Maybe that's the part that needs to be repaired. Of course, you could just measure it if your tape measure is long enough, but maybe your tape measure is only 8 meters long. So, or just, whatever reason. Anyway, we're going to do a bit of Pythagoras theorem here. No getting away from it. So we're going to label that side C. We're going to label the other two A and B. According to the theorem, C squared is equal to the A squared plus the B squared. Right, so in this case, our longest side, our hypotenuse, our C squared, is on its own. The longest side is always on its own. It's going to be X in this case, so X squared. The two shorter sides, the 8 and the 6, they're also getting squared and they're being added together. So 8 squared is 64, 6 squared is 36, adding together we're getting 100. So this thing, our Pythagoras theorem is saying is that X squared is equal to 100. We don't want to know X squared, we want to know X, so we're going to square root both sides. The square and the square root always cancel each other, don't they? So X is equal to what? Square root of 10 is, square root of 100 is 10. Okay, so X is equal to 10. So, okay, that's kind of easy enough. Next question may be slightly harder because it's worded a bit difficult. So we have this little diagram here. We've got a pylon, a guy flying a kite. That's the idea. Okay, let's read what it says. A man is flying a kite. He's 40 meters from an electrical pylon. The wires are 20 meters above the ground. The string on the kite that he's flying is 50 meters long. Is it safe to extend the string fully? The man is 1.9 meters tall, but when he raises his hands, they have a reach of 2.5 meters. Okay, so 2.5 meters. Let's see if this is safe. Well, what triangle are we talking about? So we're talking about when he has his hand fully stretched upright, all the way up to the top of the pylon. Okay, so that's what we're talking about. That triangle there. So let's sketch that triangle. And notice, of course, that's a gap of 2.5 meters, isn't it? So it's 20 meters tall for the pylon, but we could take away the 2.5 from 20. That'll give us 17.5 for the height of our orange triangle. So let's draw that triangle. We know the triangle is what? 40 meters long, 17.5 tall. It's 40 meters and 17.5. Notice how we're assuming the ground is horizontal and the pylon is vertical. So we're assuming it's a right angle, which is kind of a reasonable enough assumption. Okay, so we need to know about the 50 meters of his string. Is the 50 meters going to be too long and put him in dangers, or is it safe enough to fly? That's what we're trying to figure out. So we can use Pythagoras' theorem here. We can let the 50, which is the longest one, be on its own. So that's going to be 50 squared. And then the other two sides, the 40 has to get squared, and the 17.5 also has to get squared. So we're squaring everything. So 14 squared in our calculator is like 1600. 17.5 squared. What's that? 306.25. So that's a total of 1906.25. Okay, so is that equal to 50 squared? So 50 squared is what? 50 squared is 2,500. Okay. You can see they're not equal. That's because this thing doesn't make a triangle. Might be confusing actually to put in the 50 squared there. Maybe I should just put in my diagonal squared or whatever. what we're saying is that if we didn't label this 50, we're just trying to find out how long this is. C squared is equal to this. So how long is C on its own? That means we've got to get the square root again, yeah? Square root time. My equal signs there are not very nice. So what is the square root of 1906.25? So square root of 1906.25 is 43.66 meters. So the length of C is only 43.66 meters. 43.66. We can see that the 50 meters we had there, it's far too long. If this guy flies his kite, it's a good chance the kite could get in contact with the electrical cables and could damage the kite, could hurt him. So yeah, not good. Okay, next question. A ramp in a skate park is to be 1 meter tall, 2 meters wide, so 2 meters long and 2 meters wide. Find the length of the diagonal. So we have our diagram. Let's just draw a diagram at the side to make it easy. So it's going to be 1 meter tall, 2 meters long. So we have that, and we have our diagonal marked. So let's use Pythagoras theorem now to find the length of that ramp. Okay, the first question asks, what are the dimensions of the sheet to form the skating? We'll worry about that in a second. Sorry. How long is that diagonal? So we've labelled the long one C, as always. The hypotenuse is always the one that's on its own from our Pythagoras theorem formula. And A is 2 and B is 1. So 2 squared is 4 and 1 squared is 1. So our C squared is equal to 5. Again, we don't want to know C squared, so we'll get the square root of both sides. So C is equal to root 5, or if you want that as a decimal, it's less accurate of course, but root 5, what's that? Roughly 2.23, I should have said 2.360679777, blah blah blah. Okay, so better off at root 5. Anyway, what are the dimensions of the sheet to form the skating surface of the ramp? Okay, well the dimensions were 2 meters wide, wasn't it? The question said. And we just found the diagonal length was root 5 meters long. So they're the dimensions. So it's 2.4 by root 5 meters, 2 meters by root 5 meters. Or if we want to know that as an area, we just multiply them. As an area, it will be, 2 root 5 meters squared, because meters by meters is meters squared. Or if you wanted that as a decimal, 4.472135955. Okay, so it's a little short of 4.5 meters squared. Okay, but 2 root 5 is more accurate. The top surface is to be coated in a hard-wearing non-slip sealant. It is very expensive. €35 for 100 mils. €68 for 200 mils. Or 155 for 500 mil, so it's expensive stuff. The sealant covers 4 meters squared per 100 mil, so it doesn't have much coverage either. Okay, so that's possibly the most important information in the question, is that 4 meters per 100 mil. Okay, so it's that tells us the coverage we're getting from it. How much will the sealant cost? All prices are ex VAT, and VAT's at 21%. Okay, so let's go back. It's the top surface, so it's that calculation we did earlier. So it's the 4.47 roughly meters squared. Now that's what we need. Well, we can see from up here that using this information here, 4 meters squared per 100 means this only does 4 meters squared. Is not enough. So buying the 100 mil is no good. It looks like we want to buy the 200 mil can, doesn't it? Because 200 mils, according to this information here, that'll get us 8 meters squared. Well, that's enough. That's enough to do us, isn't it? Yeah. Yeah. So we want to buy 200 mils of this stuff. So we want to buy the €68 can. So, how much will the sealant cost? Well, it costs €68 x VAT. Okay, but we need to add on the VAT, so let's start with 68 euros. That's the full price. We'll divide by 100 to get 1%. So we're finding 1% here. That's 0.68 euros, of course. We want to know 21%, so better multiply by 21. So 0.68 multiplied by 21. That works out as 14 euros 28 for the VAT. An estimate the government gets in their consumption tax, or their value-added tax. So the total price then is the 68 plus the 14.28, gives us a total of, was it 80 something? 82 euros 28 cents, including VAT. That's the price, including the VAT. So inc VAT. Inc VAT means including VAT. Right, so we have a price including VAT. Find the volume of the ramp is the last question here. So find the volume of the ramp. So that means we're going to need to know the area of the triangle. If we can find the area of the triangle and then multiply it by that width. So we need to know the area of this triangle, which is a 1 meter by 2 meter triangle, and then multiply by the width of the ramp. So we're going to get the area first. Okay, so our area of our triangle, it's a 1 meter triangle by 2 meters. Well, the probably easiest way to get area of a triangle is to get the area of a rectangle and then divide by 2, or you can use a formula. Formula is half base by perpendicular height. That's the same thing. Okay, so if I was to look at the formula, I'd go half the base, which is 2, and the perpendicular height, which is 1. So that is, do that in the calculator. 2 by 1 is 2, and half of 2 is 1, so it's 1, and the units are meters by meters squared. So the area is 1 meter squared if I'm going with that formula. Really, I hate when I work to the right hand side. Should try and work to the left. Or actually to work down. As I said, you could do the area of the rectangle first. 2 meters by 1 meter. So the area of this triangle area is 2 by 1 length by width, just 2 meters squared. And of course you don't want the full triangle, you only want half of it. So you'd get half of that. And you're talking about 1 meter squared. So it's the same thing. So the area of the triangle is 1 meter squared. But we said we had to multiply by the width of the ramp to get the volume. Because volume is always area multiplied by the perpendicular length. In this case we're calling the perpendicular length the width of the ramp. That was 2 meters, and the area we just saw was 1 meter squared. So 2 by 1 is 2, and meters squared by meters, well there's 2 meters over here, so it's like meters, another meter over here, so that's 3 meters altogether, so it's, you know, just 3 m's multiplying each other, so it has to be cubed. Or the other way is to think about adding those powers to 2, and the invisible 1 gives you 3. Whichever way you want to get those powers, just make sure you get those powers correct. I know that adding the part doesn't make sense, because it's kind of like, I'm multiplying, why am I adding here? But you got to remember 2 meters squared here, you got 1 more here, so how many meters are multiplying each other? There's 3 of them multiplying each other. So the volume is 2 meters cubed. So we are kind of finished what we wanted to do today. We've taken a look at the sine, cosine and tangent. Along the way we heard the languages of hypotenuse, opposite and adjacent. We've covered these learning intentions. We've labelled the sides of triangles. Always start with the hypotenuse first, and then position ourselves at an angle so we can find our opposite, and the last one is the adjacent. We have a memory tool, maybe Sockatoa or silly old Harry caught a herring trawling off America, or some old hippie caught another hippie tripping on acid. We use that memory tool to remember the definitions, so when you get into an exam or a test, always write down your definitions straight away using your memory tool. Straight away you have something then to work from. And we saw that you could use those ticking. We went through sine, cos and tan, and we ticked with little ticks, so we found the one that had 3 ticks. Inverse functions, they were kind of easy. We just had to hit shift button on the calculator. And Pythagoras, we just square all three sides, put the longest side in its own squared, and the two shorter sides are together getting added. And that should be useful to do lots of problems. Okay, hope it was helpful. Thank you very much. Bye bye.